Okay, so just make sure you do the split array harder. Example there is going to help you for assignment number 1. And it's been released for almost, well, I shouldn't say almost. It's been maybe about 4 days or so, right? You really want to get started and then struggle with it. And if you want to speak to me about some hints, it will be office hour. Or if you want to approach me after class to get some quick hints, I can do that too. All right, so guys, you really have to make sure you learn this stuff from there. The credits for the assignment is guaranteed, right? It's really participation, but you gotta make sure you really spend the time doing it. Otherwise, the test, will be hard for you, right? You gotta make sure you do the work, okay? Any questions in general? You want me to clarify? All good? Okay. Let's do a very quick recap from last time, okay? So again, unfortunately, we have to stay in 2 different classrooms for Tuesday and Thursday, but hopefully now you know the pattern. We're just going to continue with that. So one type of question you have to make sure you know how to answer will be if you're given some Java code or algorithm, you are actually going to calculate the precise number of primitive operations. We did one example in the class, and this one will be here for you to exercise. But I would say the questions I put over here, they are more like a guidance question. So whenever you are solving problem like that, always keep this kind of question in your mind so it can just remind you about what will be the critical steps or strategy for you to solve the problem. Okay? And we talk about making a transition from absolute running time, which depends on the platform, about which machine or even virtual machine that you're actually executing your code or algorithm. And we're moving that towards more mathematical relative running time. So we're going to focus on just relative running time function, just like that. Right? We kind of explained last time about why we're doing this, because the extra factor, like a little t, which might vary between platforms, simply doesn't really matter. It's simply not necessary for you to make some meaningful conclusion about which algorithm might be more efficient. Right? Keep that in mind. Right? It's very important to know why we are making such transition by not considering absolute running time anymore. And then we spoke about, well, just basically different terminology, right? Talking about you should really identify the highest power. Right? In this case, it'll be a polynomial n to the power of something that will actually tell you that this running time here is going to dominate the running time overall. And everything else is considered lower terms, lower power, and then you also got things like a multiplicative constant, right? So these are the terms you want to also make sure you're familiar, and sometimes when we solve the problem, I might just refer to them, so you got to know what I'm talking about. And that's the common classes of running time function, right? Constant, logarithmic, linear, and log n. We'll definitely see n log n, not just yet. When we talk about sorting algorithm, which is quite interesting. We're going to talk about merge sort and quick sort in this course. You're going to see why the running time will end up being n log n, right? It's very interesting to see. And then quadratic, n squared, and cubic, n to the power 3, and also exponential, right? Exponential is really about you're basically doing things brute force. You're really trying out every possible ways to do things. Sometimes you may have to, sometimes you don't really have to, right? So that's something we can clarify whenever we need to. But just be aware about the different classes. Of course, constant will be the cheapest, right? And exponential will be the most expensive. And the more expensive the running time function is, the faster it will grow with respect to the input size. And we spoke about if you're given running time function, how can you determine very quickly, without even trying to prove just yet, about which one might be more efficient? Well, you simply identify the highest power. For example, if these two, the highest power, are equal, that means they're equally efficient asymptotically, meaning that when the input size goes towards infinity, we can already say which one is more efficient. That more or less equal. On the other hand, if you look at this one here, highest power is 3 here, and this one here, highest power is 2. In that way, strictly speaking, right, it is more efficient because asymptotically, towards infinity, this will just grow much more slowly than the other one. So that's why it's asymptotically more efficient. All right. And we try to define the big O, right? So that's something I'll try to visualize one more time today just as a recap. But you guys will have to make sure you get yourself familiar about the involved terms. There will be f of n. That will be the running time function for a particular algorithm you're considering. And also you got G of n, it will be the reference function. So today we're actually gonna, after we do a little bit recap, some exercises, I'm gonna talk about properties for the big O. It's also very important for you to know. Some very practical properties or common misconception we have to clarify. So G of n, and also G of n doesn't really stand by itself usually. You have to modify its slope, right, to make it a little bit steeper. We'll see, okay? I'll do one more visualization together with you. Just make sure it's 100% clear. And the goal usually is to prove that the running time function you have is a member of some big O family of the reference function, right? Visually, you want to make sure f of n belongs to this particular class of the big O family. All right, that's what we are doing. And that's the formal definition you will see in any standard textbook for algorithm or data structure, right? So if you want to show that f of n is a member of the family for g of n, right, big O. In that way, you have to choose two things to really show it. You need some multiplicative constant c here, and that one there is actually going to modify the reference function such that when you try to compare reference function and the running time function, starting from certain point, which we call n0, you're going to see that the running time function is consistently lower than the modified version of the reference function. So that's what we call the upper bound effects. All right, that's very important equation. You want to understand visually, that's showing that the running time function is always below, it's upper bounded by. On the other hand, mathematically, it's really less than or equal to, right? When you do the more formal analysis, you definitely have to go back to the very basic math, okay? And we spoke about, for example, if I give you some c and I give you some value for m0, the one we did was 1 last time. We're going to show that given c being 9 and n0 being 1, the upper bound effect hasn't really started just yet. So you want to review maybe the notes from last time to see how we can show that. All right, it's also very important. But today we're going to show you one strategy, which is very handy to see. Once you have chosen a c, according to the strategy, n0 is always guaranteed to be a certain number. We'll see today. Okay, so there's a little theorem that we're going to use right away, but I will leave the proof of that theorem maybe to Tuesday, right? So we don't need to worry too much about proof just today. We can use it right away. Any question about this definition here? Any part that's not clear to you? Very important, right? Okay. All right, so that's about last time on Tuesday. So today, I want to start with more like a recap, very quickly. So that one there really show all the three functions together in a single diagram. I think this one might be a very nice way to really recap. Okay, let's do it. I think it's worth it. Okay. So here I got f of n, also g of n, and the modified version of g of n by multiplying with the c, right? So let's now take a look very quickly. Let's start with the algorithm that we have. Right? So this is the running time of some algorithm. And then our goal is to show that, you can think about this guy here, is the reference function. Okay? So this one here is the reference function. Okay, g of n, without any manipulation just yet. What's our goal? Our goal is we want to show or prove that there's a membership right here. F of n, the running time function, is a member of the big O with the reference function g of n. So this is our goal. And let's recall intuitively. In order for this membership to be true, the upper bound effects must happen at some point, right? However, if we look at the plot over here, and by the way, I'm assuming that you can easily plot these functions, for example, an plus 5, 9n, and also n, right? So those basic stuff I can leave to you. Right? If you really got trouble plotting these functions here, please let me know. Otherwise, I assume you guys know how to do it, right? So I can go directly to the point. Now, here's a question. If you only look at the green and the pink alone, is the green ever upper bounded by the pink? No, because the green here never appears underneath it, the pink, never ever. So that's why we said that very often g of n cannot exist just by itself in your proof. You have to choose the c. Right? First point, okay? So let's now see this. So I'm going to say right here, f of n is never upper bounded by g of n itself. Right? It's a very important point for you to realize right away. That's why for you as an engineer to prove it, you have to choose the c. Right? Let's say in this case we choose the c to be 9. All right? So this is the c chosen by the prover, which will be you. All right? So once you have chosen that, you can see that it's going to basically modify the slope of g of n. It's going to be from here to something that's steeper right here. As soon as we have that, we know that there will be certain points starting from which we're going to get upper bound effects. All right? So let's now highlight it. So now over here, right here. So now we can now focus on this running time function and the modified version of g of n. However, the upper bound effect does not happen all the time. For example, if you look at just this part, right? So this will be the cutting point. To the left of it, you can see that the green one, the running time, is never upper bounded by the blue one. So this point is not a starting point, right? To the left of that. It's really starting from this point. Okay, let's write it down. So what we should do is, let's now isolate that middle point right here. Okay, so what we have is, so to its left, right here. So I want to say, when n is strictly less than 5, f of n is not upper bounded by c times g of n. More precisely, f of n less than or equal to the 9 times g of n is always false. Okay? Upper bound effect simply doesn't occur, not just yet. However, if you actually try to count from, let's say over here, starting from 5 itself and towards infinity, right here, right? Just towards infinity. This part here is where the upper bound effect will always be the case, right? As long as there's such a point that you're okay. Doesn't matter how large that point might be, as long as it exists. So this part here, when n is larger than or equal to n0, f of n less than or equal to c times g of n is always true. All right? So this is really consistent with what we spoke about last time, is like a formal definition. I think this one here just have a very concrete example to really see. All right? Of course, you got to make sure you really understand what's going on here. In the test or the exam, I might just pick some details from here and make some variation of that to ask you to assess your understanding. Right? Just make sure you study carefully. Right? Any questions, please? Okay, if you guys feel comfortable, and then let's move on. Okay. And by the way, this page here corresponds to slide number 25. Okay, just in case you're wondering, you can definitely study this slide as well. Okay. So right now, let me mention about this one here. So this will be, let me see which slide it is. So let's go back to the slide. Okay, slide number 25 is what we just visualized. And then what I'm going to talk about right now is slide number 26. So slide number 26 talks about a theorem for you to somehow choose the C and N0 almost like automatically, and it's guaranteed to work. Okay. There are two parts about this slide over here. Number one, you should learn about what the theorem should be applied, which we'll do today. Part two, which is also quite handy, is to see why this theorem is actually true. That's something maybe we can do in the beginning of our next Tuesday, okay, in the Aquadet East, okay, a different context for you, okay. We'll do that. But for today, just learn about the theorem and how to use it. We'll do an example, okay. Let's read it together, okay. Our goal is to prove that the running time function is a member of the big O family of reference function g of n, right? So now we say that if, this is important assumption, okay, be careful. If the running time function here, okay, let's just remind you here, if the running time function is a polynomial of degree d, polynomial of degree d simply is n to the power of something. Okay, I'll give you one violation, which is not a polynomial, log, for example. So this theorem here, strictly speaking, does not really work when you are running time involving log. Not always, but I would say you can get a very good guess from there, but you got to always verify. We'll do an example to show you what I mean. Okay, so let's now write down the common exception, right? You want to be aware. Okay, not log. Okay, we'll see. Okay, I just want to make a quick notes. Oh, I didn't. All right, guys, please, you don't need to be polite in this case. Just shout to me to say I got to switch, right? Okay, that's okay. All right, so we say that if f of n, the running time function here, is a polynomial of degree d, all right? So the only exception is log, all right? So whenever you got log in the running time function, you can still try to apply this one here, but be careful, you got to make sure you verify, okay? Okay, and let's say this is the running time function over here, right? So somehow we try to arrange in a different way. We'll say polynomial, okay? So the polynomial is really here. N to the power of 0, n to the power of 1. You can think about we can arrange that in the increasing order from 0 all the way to the highest power. Highest power can be 2, can be 3, can be 100, right? Just some number, okay? So this you can think about is the highest power. Okay, the d here is the highest power. As soon as you identify the highest power, you can say that it's going to be big O of that particular highest power. So you can think about d here really just correspond to the d right here. All right, so that's about how you can identify the highest power in the polynomial and say that it's a big O of that particular polynomial, right? And then, how do we prove this, right? In order to prove the big O, we know that we need, by definition, we need a C and the n0, okay? Assuming that it's all about n to the power of something in the whole running time function, right? The C here will be the sum of the absolute value for all the multiplicative constant. The sum of absolute value of all the multiplicative constant. For example, you can see that here. A0, A1, all the way to AD, right? Just symbolically, right? You should put all of them in the absolute value because the multiplicative constant could be negative. That's why you got to put absolute value. All right, just be careful. Okay. And then, very conveniently, the n0 guaranteed to be 1. Guaranteed. However, in the case where you have log in your running time function, you have to verify. You verify pass, good. If it doesn't pass, you have to try it out, maybe another value. Okay, I'll write it down. And then we'll do example right away. Okay, so n0 over here, verify particularly when the f of n involves log. Okay, just make that notes. Any questions just about how to read this theorem? Everybody okay? Right? We just need to apply that to examples today, right? And the empty part is just about proving it, but I think it's really also worth doing as well. For those of you who might be interested, you can give it a try maybe before Tuesday. It's really a nice math exercise. It can give you some insight into why this theorem will actually just work, right? And then I'll go over the proof together with you on Tuesday in the beginning. Okay? It wouldn't take long, but it's nice for you to try. Okay. Right, let's now apply this theorem right away. Okay. Let's do this one here. And this can be a very typical, I would say, on the maybe the easier side of the question I might give to you in the test or exam, right? Let's make sure you can do it, right? So what we have is, we say, we want to prove this particular running time function here, and you can see that there is no log. So we can quite confidently apply that particular theorem. But I would say verify anyway. It wouldn't take you more than a few seconds, maybe no more than 30 seconds to verify that, right? I would suggest verify always, okay? So look at this running time function here. And then we want to prove that it is big O of n to the power of 4. And not surprising, because 4 over here correspond to the highest power 4. Agree? Okay. Let's now identify that very quickly, and then I'll show you the steps. Think about the 4 over here is really correspond to the 4 over here. So that is the highest power. Okay. Highest power. All right. And another important thing for us to also remember, n to the power of 4 over here is indeed the g of n that we talk about usually. Also very important. I think maybe your fellow student from the previous term, sometimes they kind of forget about where the g of n is, because when you want to show the upper bound effects, you have to apply g of n on the right-hand side, right? That's something we'll see. Just always make a note to yourself, okay? Okay, let me write it down again, and then we'll see how we can prove it. First of all, let's see this. You don't really have to like a sort, like a polynomial degree always. You don't need to. But this way, what's given to you is already sorted. So 5 times n to the power 4 minus 3n to the power 3 plus 2n squared minus 4n plus n. I'm just going to rewrite it to you. 1 times n to the power 0. Agree? Right? N to the power 0 is simply 1. Okay? Sometimes by explicitly writing n to the power 0 can actually help you identify some pattern. Not in this example specifically, but maybe for later, which I'll show to you a little bit later. Okay? And, okay, so number 1, we already know we can already approximate that's the highest power. F of n is big O of n to the power 4. Well, this first part here is not strictly necessary. That's already given to you. But I just want to say that, right? It's really where that comes from. But now how do we prove it? We have to prove it by choosing the C and N zero. We want to prove by choosing C and N0. And just remember from the theorem, it's actually going to be the absolute value of all the multiplicative constant, right? What are the multiplicative constant in this case? We got 5 minus 3, right? Plus 2 minus 4 and 1. You got to put each one of them into absolute value. Okay, that's what we're going to do. Okay, so we're going to say number 1, we have the C, which will be equal to 5 plus minus 3 plus 2 plus minus 4 plus the 1 right here. All right? And it's 15. All right? N0 guarantee in this case, because there's no log, will be just 1. But let's verify. Okay. I just want you to get very explicit again, practicing about how to state the upper bound effects. Okay, so we talk about the C and also N0. Right, these two. And we got 15 and 1. And verify right here. First of all, what exactly are we verifying? We want to make sure the upper bound effect is going to happen at exactly the N0 we have chosen. The upper bound effects occurs from N0 equals 1. That's what we are trying to verify. Okay, it's also very important about this one here. How do we formulate it, right, mathematically? We know visually what that really means. That simply means starting from this particular point, it should be this, right? That's something we kind of recap. Okay, let's now do it together. We can do a little bit more slowly for the first time. You can say f of n0 should be less than or equal to the c we have chosen multiply g of n0. Since this is the very first time you're trying to verify, so I just try to give you one more step to start with, right? Once you get more comfortable, you don't necessarily have to start with this, right? But before you get comfortable, this is worth writing. And let's now plug in the numbers. F of n is here. And n0, in our case, is simply just 1. Okay? So if you try to say f of 1, right here, it's going to be 5 minus 3 plus 2 minus 4 plus 1, which makes sense because 1 to the power of 4, 1 to the power of 3 is simply just 1. Right? That one, hopefully you're comfortable. Right? And then we're checking to see whether or not it's less than or equal to the right-hand side. Right? The c we have chosen is 15, right here. And g of n, right here, 1 to the power of 4. I'll write it down explicitly. 1 to the power of 4. All right? And then for this part over here, it's quite obvious. This one here will just satisfy, right? 2, 4, 0, 1, right? 1 less than or equal to 15, true. So upper bound, in fact, indeed is there. So verification, done. There's no need to adjust the value for n0. But we shouldn't need to because this running time function here does not involve log. Okay. Question? It's not too bad, right? Now, things can get tricky, but one step at a time. Okay, so why don't we do maybe a few more, and then we can talk about properties maybe after the break. Okay. All right, for now, I'll just keep it temporarily. We'll come back. Question?
Why did you multiply by 1 to the power 4?
Which one? You mean here? This one here, right? Okay. The reason is, if you think about this is a general equation, it should be the multiplicative constant we have chosen, which is 15. So that's a 15 here. And then g of n, 0, will be g of 1 in this case. But g of n itself is n to the power of 4. So that's 1 to the power of 4. So you just write it down explicitly, because it may not be just 1 to the power of 4 always, right? It depends on what g of n is. Does that answer your question?
Why 4?
Hmm?
Why 4?
So, right? Remember, we are saying that this running time function here is big O of n to the power of 4. So this is a g of n, right? The reference function. That's why. It's a good question, but so always be clear about what g of n is. Any questions before I move on to do more examples? Yeah, please. That's a good question. Okay. I like the precision. Okay. Why don't we say this? You can say that if you look at this one here, think about n to the power of 4 is what we call the highest term. Because the 4 here is the highest power. Because 4 itself is the highest number for the exponent, right? Good. Okay, let's do more. Okay, I'll just skip these pages temporarily. Okay, let's do one example here. Well, you can see here we got log, right? But that's okay. We just got to be careful. We know that we can still try to apply that theorem, but we got to make sure we really verify. Okay, I got 2 log example for today. Let's do the first one together, and I'll let you guys take some time, do the second one, and then we'll discuss. All right? Okay, this one here. Question number 1. What's the most accurate asymptotic upper bound? Basically, look at the highest power, right? That's something we kind of did last time. What highest power? N log n squared, n squared, agree? Okay, that's something we actually did, before. So you can also look up the notes from before. Okay, n squared, highest power or highest term, right? All right, so question 1. Big O of n squared is a very educated guess, right? It's not random guess. And let's now do it right away. The n squared over here is the g of n. Later on, when we have to verify if the upper bound in fact is there, we have to use the n squared rather than n to the power 4, right? So g of n is different, right? Okay, second part, which is definitely more important. How do we prove the claim, okay? For now, we just keep in mind we got log, right? Oh, another thing, maybe I mentioned earlier, I don't quite remember. So whenever we say log n in this course, if I didn't tell you explicitly about the base, it would be base 2, okay? If I did say that, I'll emphasize again. It will simply just be log base 2 and then n, okay, for this course, okay? If it has to be base 3, base 10, other base, I'll let you know explicitly in the question, okay? So what we do is we want to choose the C and choose the N0. If we follow the strategy, N0 should be 1, but we're going to verify, subject to verification. How about the C here? Let's identify multiplicative constant. So we got 5, we got plus 3, right? And notice that plus 3 is applied to n log n, right? And also we got 2. And then we got 5. So there's no tricky thing about the multiplicative constant, just all positive. But I would say to be very kind of faithful to the theorem, let's put the absolute value anyway, to be very explicit. Okay? So we can say it is 5 plus 3 plus 2 plus 5. 15. Okay? Just happen to be the same as before. Doesn't need to be, right? Just happen to be. All right, and the N0 will be 1. So now we got to verify. Okay? So now let's verify. Okay, remember the very first equation there from before. I'll just show you very quickly. Right here. Let me write it down one more time, okay? So what we have to make sure is f of n0 should be less than or equal to c times the g of n0. In our case, it will be the f of 1 less than or equal to 15 multiplied by the g of 1, right? So now, let's try to do some simplification. F of 1, right here, basically, just apply into this function here, right? Let me put star. F of 1 will be 5 times 1 squared plus 3 times 1 times log 1, okay? Plus 2 times 1 plus 5. Agree? Okay? If I make any mistake, please let me know, okay? And by the way, what is this? 0, agree? All right? Because log of 1 is always 0 because 2 to the power of 0 equals 1, right? I'm pretty sure this might be one of the easy facts you learned maybe from the calculus class, right? Please review, right? All right, so that part there is 0, okay? That part there is 0, okay? So we got 5 plus 0 plus 2 plus 5, okay? And that one there is going to give us, okay, so 5, 7, 12. Okay. And what about the right-hand side? The right-hand side over there, okay, star, star. Star, star. So we got 15 multiply g of 1. All right. Any suggestion? Maybe from you, since you kind of asked me about for the previous page. How should I simplify that into? 15 times what? 1 to the power, yeah, exactly, right? Because now it's a square right here. Awesome. Now you got it, right? 2, so that would be 15. All right, all good. So now we are basically asking 12 less than or equal to 15. True, we're good. Okay. So verification pass. So indeed, we can simply use C and N0 being these two values as the proof. Okay. If you look back to the definition for big O, the N0 must be strictly larger than 0. That's by definition, right? So by using the theorem, that can it can show you the smallest N0 possible, which is 1. But if you got log, the smallest value for N0 may not necessarily be 1 always. Okay. Guys, how about before we take a break, why don't we do one more example? This one. Can you guys take 1 minute or 2? Give it a try, and then we'll go over. How about that? This one looks very similar to the one we just did together, but just follow the steps and then just be faithful about what I said what you should really do. Let's see. If you already got to the point where you got C and N0, of course, you gotta verify, right? If you're still not exactly comfortable about the process, just make sure you practice, right? I do have a few exercises here. I'll leave empty. You can practice. You can see the solution on the slides too. Okay. Okay, one moment, and then we'll go over it, and then we'll take a break. Okay. And of course, I can rewrite this term here to be 2 to the power of N0, right? All right, let's take a look. Okay. Part 1. What's the highest power? What's the highest term? Is it this one here or log n? Which one grows faster? Log n, right? Okay, remember constant is completely flat. Log n, almost flat, but not exactly flat, right? That's the way I kind of remember. Good? Okay. So for part 1, big O of n to the power of 0. Oh, log n, did I say, okay, gotta make sure, okay. Just in case I said anything wrong, okay, let's double check, okay. I do apologize for the confusion. This is the constant, right? Log n is actually a little bit faster than that. So log n is the highest power. Okay, yeah, I don't want to create any confusion to you. Okay, very good. So number 1, oh, sorry, not this one here. There we go. Big O of log n. Okay? So this one here is the highest term. Okay? And then this one here will be the g of n, right? Again, be very explicit. Okay, number 2. Okay, let's just apply the theorem. So we're going to choose c to be multiplicative constant, 3 here, and also 2 here, right? It's going to be 3 and 2, which will be 5. Okay, hopefully at least you got to that point, right? And then n0 will just be 1 by the theorem, but now we have to verify. All right, for those of you who already maybe got to that point already, you will see that verification will fail. Okay, so that's why I really want to make sure we do this example together to convince you. Okay, let's see. So what we do is we want to check to see f of 1 less than or equal to the c, which will be 5, multiply the g of 1, right? And then the f of 1 right here will be 3 times log 1 plus 2, right? And then 5 times g of 1, because g of n is log n purely. That would be 5 times log 1, right? Let's do a little bit of simplification. So you will see that this will be 3 times 0, because log 1 is 0, plus 2, 2. And this one will be 5 times 0, which will be 0. And 2 less than or equal to 0 is false. It's a very valuable information. That means the n0 is not the right value. You've got to be something bigger. Okay, so in this kind of situation, what you should do is you should just try something bigger. Maybe try n0 equals 2. You usually wouldn't take too long for you to get to the right value, right? So I'll give you as exercise. Okay. So the next step. The exercise is try n0 equals 2. If that one doesn't work, for example, you can try 3, and then so on. You wouldn't take. Don't worry. It's not gonna take indefinitely for you to get there, right? Questions so far? Yes, please go ahead. Good question. So you're right, strictly speaking. So this is only one value, but since the way we're going to choose the multiplicative constant, if this one already work, then it's guaranteed any larger value is going to work as well. We're just going to leave that kind of implicit. That's why. You can think about the value we're trying to prove is the smallest input value size, where we got the upper bound effects. Any larger input size guarantee is going to have the upper bound effects.
So how do we know that most accurate value is an integer? If it's like 1.5.
You mean here? You mean n0 here? Good question. I like that question here. The reason is, by definition, let's go back. Let's verify ourselves. Okay, so if you go back to the definition here, constant must be integer. So think about n0. Okay, it's a very good question. Think about intuitively. n0 is the starting input size. We only say array is of length 1. You wouldn't say array length is 1.5, right? Yeah, question, please.
Would we be able to use the same strategy that we used in the last class for finding n0 instead of like doing it, increasing it?
Absolutely. Okay, guys, it's a very good question. Very good question. Your fellow student basically was asking, is it absolutely necessary for us to follow the strategy right here? Can we simply choose some c and n0, which is just going to work with upper bound effects? The answer is yes, it is okay for you to do so. But very likely, if I phrase the question, okay, let me make it explicit to everybody, okay? So let's say the question is proof. Let me make this point and then we'll take a break. If I want you to prove that f of n is the big O of g of n. Okay, let's say we want you to prove. If there is a constraint that n0 should be the smallest possible, that way, you may just want to use a strategy, because that one they can lead you to n0 equals 1 or something a little bit bigger, right? But if I didn't say any constraint, you can choose whatever pair you like, okay? Then use the strategy. Otherwise, just choose C and N0 pair that works either way. All right. All right, why don't we take a break? Okay, so we did 2 examples so far about proving big O. So for number 2 here, and also number 4 and 5, I'll leave those to you as exercises, but you can also look at the slides. I'll also give you maybe the solution, like a pages as well. But please give it a try. They are not difficult, given what we have done. And then you can look at a solution later. Okay. So I think now there are 2 more things I want to talk about for asymptotic analysis before we got to another topic, right? There'll be a new set of slides. We need to talk about some mathematical properties for big O. And also we need to see how we can apply the big O concept into coding, like a Java. That's really one of the very important learning outcomes for this course, to see how you can analyze data structures or algorithm formally. I would suggest we leave maybe the mathematical property for big O to the beginning, maybe on Tuesday. So for the rest of today, let's get the coding together with big O. That could be a little bit more motivating to actually stay. How about we do that, okay? Okay, so this will be the first one, right? So the idea is, you're given a piece of code. This code may be something that's simply given to you. Maybe you're working a team, and then your colleague told you that this is the algorithm I came up with. What's the running time? That's one way, right? Another way, you're given a problem to solve, and then you kind of sketch out this Java solution. You're wondering how efficient is my algorithm, and that's another way. You can just look at that and try to figure out running time, okay? So we are now only to approximate the running time, which means we don't really have to count the precise number of primitive operations at this point. But of course, you guys will have to know how to do it. That's something we already covered. Okay? We got many examples just for you to get some feel. Okay? So when we say determine, this will be to approximate. Okay, and then just remember intuitively, when you talk about asymptotic upper bound, you're really asking what's the maximum number of primitive operations involved. Which means you have to look at the code very carefully. I would say almost always you have to look at line by line. And of course, sometimes you may have to consider one block of code at a time. Well, it kind of depends. Okay, let's look at that. We start from something very simple, and then we do something a bit more tricky, right? We'll see how much we can do. All right, so this one here, we're simply trying to compare, well, we're given, let's say, 2 numbers, return what's the maximum. Well, I'm pretty sure you guys know, right? Maybe from 1021 or even 1011, okay? How do we analyze this, right? Line by line. If you look at line number 1 here, it's only about variable assignments, constant. I can put 1 here. Line number 3, this is about relational comparison. That's also 1. And also we got variable assignments and also 1. Return over here, by definition, is also primitive operation. You might be wondering, isn't it the case that this if condition here may be true or false, right? In the case where it is true, yes, we're going to execute line number 4. When it is false, we don't really we can skip this line. But remember, we're always approximating based on worst case scenario. So you got to think about if that line is also executed, go ahead and analyze that as well. One thing I will also suggest, when you are actually analyzing the running time, you don't really you don't necessarily have to understand the logic of the code completely. You just look at every line there and analyze how many running primitive operation. It's kind of independent concern. Okay. All right, so this one here, I'll simply write it out. You can say it is the big O of, okay. I'll write a bit reverse in a way, just to show to you, okay. This one here is line number 2. This one here, line number 3. This is line number 4. This is line number 6, okay. Which will be 4, of course. That'll be 4 times n to the 0, right? If you drop the multiplicative constant 4, it is big O of n to the power 0. Or you can say big O of 1. This or this. If you say n to the power 0 as a g of n, that's fine. But usually you wouldn't do that, right? I would say only write n to the power 0 when you have to use it to analyze the pattern. Okay. Question about this? Simple one, right? Just get a feel about what we're doing. All right, this is your old friend, find max, right? The last time we did this example here is to calculate the precise number of primitive operation. But now we have a different purpose. We just want to approximate. Okay, let's do this one as well. Okay. Again, line by line. This line here, as you can see, variable assignments, array indexing. I got 2 primitive operations, I know. But I don't need to say 2 because it's not the purpose right now. I can just say 1. Still constant. And then I can also look at line number 7 over here. I'll skip the loop just for now, right? Just simply sort out the things that's immediately obvious. Line number 7 is return. So I will also say 1. All right, so now we want to train you a little bit better just about whenever you got loop or even nested loop, right? You want to think in this way. If I look at the header of the loop right here. So this is the loop right here. And we say that what's enclosed within the brackets over here will be the body of the loop, okay? So you can think about this part here is the body of the for loop, okay? The number of times line number 4 to line number 6 is executed depends on the loop counter I, right? Because I is going to determine how many iterations we have. Agree? So you can think about each time we execute a loop for 1 iteration, we have to execute a whole block, right? What about just individual execution for that block? For that one there, you can see we got array indexing, we got relational, and then we got assignments, we got array indexing, and of course plus plus, it will be as if we say I equals I plus 1, right? That one there is also equal and then plus, also 1, right? So altogether, this part over here is simply just constant by itself, right? Every time you execute it, it's going to be constant, okay? So that one there is really just 1. However, you got to be careful because this block here, there's no guarantee about how many times it might be executed, right? It might be executed none of, like a 0 time if the loop is never entered, or it might be actually executed maybe more than that. In this case, how many times is it going to be executed, this block? How many times? Just for that. Anyone? Yes? N times, okay. How about we make it a little bit precise? N is not exactly wrong because n, n minus 1, n plus 1, right? They are all asymptotically the same. But let's be more precise. Exactly how many times? Why n minus 1? Yeah, exactly. So you go 1 all the way to n minus 1 because when I is equal to n, it's going to be false for the condition. So you don't even enter the loop, right? Okay, good. So this one is pretty easy, but I'm going to write it down here. So here we got I equals 0 all the way to, beg your pardon, 1. I equals 1 all the way to I equals n minus 1. And this one is obvious. We got n minus 1 iterations. And each iteration is going to execute this block. Each execution is going to be 1. All right, let's now sum them up. It's going to be big O. 1 here is going to be just line number 2. Plus the return at the end, which will be line number 7. All right. The middle will be the loop itself. It's going to be number of execution and then the cost for each iteration. So it's going to be n minus 1 multiplied by 1. So this one here, n minus 1, is about the number of iterations. And the 1 here is the block between line number 4 to line number 6. Okay? Good. And that one there, of course, you can do all sorts of simplification. It's going to be big O, n minus 1 plus 1 plus 1. Right? Just big O of n. Linear. Question?
Can we also add another plus n for line 3?
For line number 3? Oh, I see what you mean. So here we are more, yeah, it's good. Because we are now approximating, right? So we are basically saying whenever you have a loop, the way to approximate the loop is just considering how many times the body of the loop, which is going to be the most costly one. So we're going to look at that and see how many iterations you will need. Just multiply them. Yeah. So there might be some, I know what you mean. So it could be that how many times we got to evaluate this condition here and also initialization. When you have to count a precise number, yes, you got to consider them. But when you approximate, you can focus more just on the body of the loop to approximate. Yeah. All right, questions? Okay. Okay. It's going to get a little bit more sophisticated as we go, but let's do one thing at a time. Okay. Okay, so before that, I would like to talk about a little formula for you guys to also use, okay? Because later on, we're going to see some example where the pattern for the loop counter may not be so obvious, so you will need something to help you, all right? So we want to actually calculate the size of some interval, okay? I'll write it down. So when you have the size of some interval a and b. All right. So here a and b are integers. And typically a will be less than or equal to b. Typically. Okay. If there are exceptional cases, we can talk about it. But for now, you can assume a should be less than or equal to b. Okay. For example, I might ask you about what's the size of, let's say, from 1 to 4. I'm basically asking how many numbers are there in the interval. And also another thing to mention, the square brackets as opposed to parentheses. Right? That's something you guys saw in the previous math class, right? So the square bracket here simply say it's closed interval, meaning that n values should be included. Closed interval, which means the end values a and b should be included. So here, when we say 1, 4, it's really asking about how many numbers are there between 1, 2, 3, and 4. Right? That should be 4. Right? Of course, a and b can be arbitrary number. Right? So that's something we want to learn. Okay? So here's a little formula. The size of that would just be b minus a plus 1. Okay, let's verify that very quickly. I can give you a little bit of visual justification. Not really proof, just justification. Okay. So b minus a plus 1, right? For example, if I have, let's say, how many numbers are there between 3 and 99? Of course, you don't want to count by your fingers, right? You want to see exactly. All right. By applying the formula, we got 99 minus 3 plus 1. We got 97 numbers in total. Basically, you're asking going from 3 and 4 all the way to 99. All right. That's one. Another one would be if I got, let's say, 0 to 99. This one is actually more relevant to what you learned earlier. We're basically asking, let's say you have an array. Minimum index is always 0. And the maximum index is actually 99. I'm now asking you, what's the length of the array? All right, that one may be a little bit easier. So what's the length of the array? 100, right? Okay, good. That was kind of easy, but it can also be applicable, right? So this one could be more like a array with the maximum index 99. And that one there, you can simply use 99 minus 0 plus 1, which will give you 100. All right. Let's do a very quick visual justification, and then we'll move on to the next example. The way you can think about it is like this. Let's say this is your number line, right? Let's say this is 0. Oh, and also typically, A will be larger than or equal to 0, and also B will be larger than or equal to 0, right? It will still work if that's negative, but that's okay. Let's focus on something that's not negative. So if I have, let's say, B here, and I have A here, all right? B here simply means we have B numbers from 1 to B. For example, if I actually got B being 10, for example, so go from 1 to 10, I got exactly 10 numbers, right? Similarly, if I look at the other end, right here, A here, that means I got A numbers from 1 to A. So now my goal is I want to see how many numbers are there from A to B, including A, right? If I simply say B minus A, in that way, I'm effectively subtracting this part here and this part here. If I try to do B minus A, I'm excluding A already. I should add it back. All right? If I say B minus A here, somehow A is excluded. And it should be added back. Okay, so that is why this formula here, plus 1. All right? Maybe you have seen that before, maybe in the math class, but this is a very quick justification. You know, minus 1 plus 1 is actually very critical when you actually want to figure out the number of iterations. Okay? Questions about this? Okay, okay, think about this, you know. It's, you need to be precise whenever you're doing analysis. All right, so now, let's now do another example, okay? This one here, a little bit trickier because we got nested loop, right? And if you look at the nested loop right here, we got here, and also we got, that's the outer loop, that's the inner loop, okay? And then you can see that, okay, how about this? Take a look at the brackets of this code over here, right? We basically want to figure out from line number 4 to line number 7, for example. Line number 8, of course, will just be executed once, just a return. You can only return once. But from line number 4 to line number 7, they are not really executed the same number of times. You have to see which one is considered the body for the outer loop or the inner loop, right? Take a look at the bracket here and make some decision for yourself, and then I'll go over that. That's a critical point to see. If that might help, think about bracket here correspond to the bracket here, right? Also, the bracket here correspond to the bracket here, right? And if you look at this one here, I++, this one here, the number of execution depends on just the outer loop, just the I. Are you okay with it? Right? Question. What about this part here? I'm going to highlight the remaining part. This line here, it's more like an if statement. Of course, we're considering worst case scenario. Just assume, consider the case where if statement would be executed every time, like being true in the branch. And line number 4 to 6. So these are considered the body for the inner loop. Okay, so that's the body of the inner loop. Now the question is, how many times, let's start with something simple. How many times will line number 7 be executed? Yeah, go ahead. N times, because the pink line, line number 2, is the outer loop, right? Okay, that's very good. That's something we'll keep in mind. Okay, I'll get there. Okay. So that one there, outer loop, and the I will just be from 0 all the way to n minus 1, right? Because it's strictly less than n, so the last value will be n minus 1. And the little formula we have from 0 to n minus 1, you will simply get n minus 1 minus 0 plus 1. That'll be n. That's exactly n iterations. So that little formula is very handy for you to see exactly how many iterations. So we have figured out for line number 7 is going to be executed exactly n times, because the outer loop is going to run n times. And of course, each time is going to cost just 1. All right. And for this part over here, you can see that it's just about relational, logical array indexing, relational array indexing, some return, and also some assignments, plus, etc., right? So this block here by itself is also just 1. But now the question is, how many times is this green block from line number 4 to 6 going to be executed? Go ahead. I agree with you, the final answer. Okay, I like that. For this particular case, I would say it's not tricky at all, because somehow you can just see that because I will be from 0 to n, j will also be from 0 to n times n, absolutely. But you will see later in some tricky scenario, j value may depend on I value itself. In that case, it's not exactly that straightforward. But for this one, let's make it slightly more complicated, slightly. But that can really help on the general pattern. Okay. So now I'm going to write something here, and then we'll figure out. Okay. So the number of times this block is executed depends on combinations of I and j. So we got j here, and also we got I here. So what we do now is to enumerate the possibility very quickly. So that will be a very good warm-up exercise for later, right? For this particular one here, it's not strictly necessary because it's really from 0 to n, 0 to n. It's quite straightforward, but I would suggest we do that anyway, just to get things clear, all right? So what I will do is, so now based on these two headers, so this one here, oh, sorry. Let's say based on this one here, and also this one here, okay? We're going to figure out the pattern of loop counters, two loop counters, I and j. Okay, let's see. Okay, outer loop is more like constructing a table of 2 dimensions because now we got 2 loop counters, so 2 dimensions. If you got triple nested loop, of course you got 3 dimensions. Right? That's for later. Okay, so let's talk about I first. So I here can be starting from 0 all the way to n minus 1, right? Is going to be 0, 1, and 2 all the way to n minus 1, okay? And we can see right away here, right here, the number of iterations for the outer loop will be 0 to n minus 1, which will be just n, right? That's something we calculated. Okay, first dimension. For every value of I, there will be a range of values for j as well as an inner loop, right? And then the j here, let's use orange. The j here, okay, you can see j itself does not depend on I. You just start from 0 always, right? Go from 0 all the way to n minus 1 as well, right? So we got 0 here, 1, and 2, all the way to n minus 1. Okay, good for that? Okay, just about iterations, okay? And then also for I is equal to 1, also 0, 1, 2, all the way to n minus 1. Also 0, 1, 2, all the way to n minus 1, right? And the last iteration as well, right? 0, 1, 2, all the way to n minus 1, right? Think about this table here, tells you explicitly about how the I and j are going to change, right? Okay, let's now try to see how we can, well, it's very nice if you can come up with this table, right, based on the code. But the next step is to how to interpret this table. That's also very important. Okay, let's see. Because we want to know exactly how many times this block will be executed. Basically, for every combination of I and j, when it's 0, 0, this block is going to be executed once. When it is equal to 0, 2, for example, it's also going to be executed once as well for every combination. All right? So I'll give you one note here. For example, think about 0 and also 2, let's say. Each combination of ij corresponds to 1 execution of line number 4 to line number 7. Okay. Oh, sorry, line number 6, 4 to 6. Line number 4 to line number 6. All right, let's now figure out. When I is equal to 0, how many times are we going to execute this block here? We're just counting how many numbers are there between 0 and n minus 1, right? So this one here is going to be 0 and then n minus 1. So that would be exactly n times. This is saying when the outer loop has the value of I being equal to 0, it will end up, this block over here is going to be executed n times because the j value is going to go from 0 to n minus 1, which would be n times, right? Similarly, for the next row, all identical, right? So this is not really tricky for this example, okay? And for here, it's also 0 all the way to n minus 1, 0 all the way to n minus 1, and also 0 all the way to n minus 1, right? It's all n. Okay? Right here. Overall, how many times? As you correctly pointed out, n squared, right? It's really calculated area for this rectangle, another way to see it, right? Okay, so now we can actually summarize it, right? To sum up all the running time. So what I would do is, I'm going to say big O of, all right here. First of all, I would say this part here is simply 1. So that would be line number 4 to line number 6 multiplied by n squared. Okay, the n squared over here is about the number of combinations of I and j, which we figure out, right? It will be n times n, okay? And then plus. Just about line number 7 here is going to be executed exactly n times, just for according to the outer loop, right? It's going to be 1 times n. So the 1 here corresponds to line number 7. The n here is about the number of iterations of the outer loop. Okay? And then finally, we have the return statement. Just don't leave that out. And then we get plus 1. And that one there is line number 8. Okay? Sum them up, right? And then we simply got big O of n squared plus n plus 1. And highest power, 2. Big O of n squared. Okay? So that's the ultimate result for this code here, algorithm. This is a very nice kind of look ahead, for some example that we still have to see. Give me 30 seconds, please. I'm running out of time. Time flies. Okay. So this example here, please study that carefully. So on next Tuesday, we have to do another example that's similar loop, but here over there the counter pattern will be a little bit different, a little bit trickier to figure out. All right. Thank you. I'll see you on next Tuesday.